Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate combinatorics based on my book, Invitation to Combinatorics. This particular lecture is the first lecture in a sequence of lectures on generating functions. Here we talk about ordinary generating functions, and we basically just gives definitions and some examples. This is based on section 9.1. And it's the first of 3 short videos on that section. So let's get started. In combinatorics, we often are interested in a sequence of integers, h0, h1, h2, all hn, and so forth. And these usually come from a counting problem. So we are counting something and we get a sequence of numbers. Now, sometimes we're very lucky and we can get actually a closed, nice formula for hn. And that will solve the problem. We know how to find what hn is, but sometimes we can't. A popular thing that we have been doing is to find a recurrence relation for hn. And if we can find a recurrence relation for hn, if we can write hn in terms of the previous versions of hn, then we can use that recurrence relation to generate data and find hn for small values of n. From that, we might be able to find patterns, and that those patterns might be formulas, but they might be other things. They might be inequalities, they might be asymptotics, they might be other things, that information that we can glean from that pattern. And then we can prove that pattern using induction and using our recurrence relation. Induction and recurrence relations go together very well, since recurrence relations give you hn in terms of maybe hn minus 1 and hn minus 2 and an hn minus 3, then they are very useful for proving things by induction. Here, though, we're going to turn to a different method altogether. We're going to look at the powerful technique of generating function. So what we're going to do is we're going to do something that on the face of it seems like a tall order. What we're going to do is we're going to write a power series where the coefficients are those that sequence of integers that we were interested in. So we're going to write the power series g of x, and the coefficients we use for that power series, h0 plus h1x plus h2x squared, and so forth, those are exactly the sequence we were interested in. And our point here is that maybe we are lucky and we can find a closed form for g of x. We can write this power series in a closed form function, and then we can deduce information about the sequence of integers from that closed form for the function g of x. Again, this seems like a tall order, because if we couldn't find a formula for hn, if we couldn't find other things about hn, then how are we going to deal with finding this whole power series that encapsulates all of hn, every element of hn, at once? It just seems like this is a much harder problem to do than dealing with hn itself, and it's not clear how you might do that without actually knowing exactly what each one of the elements of hn are. But we shall see that actually does happen, and it's pretty powerful and amazing when it happens. So let's give a slightly more formal definition. So if you have a sequence h0, h1 through hn, and so on, we define a power series g of x, and it's going to be h0 plus h1x plus h2x squared plus hnx to the n, and so forth. So hn is going to be the coefficient of xn, and we call this the ordinary generating function for that sequence, or another name for it is ordinary power series of that sequence. So we're given a sequence, we create a power series, and it's called the ordinary generating function, or the ordinary power series for that sequence. And the notation that I will use is that G is the OPS, ordinary power series, for the sequence hn and going from 0 to infinity. This is a notation that's used often, but it's not standard. Not everyone uses this, but I like to use that. Okay, so let's start with an example. For example, you might consider the sequence of the reciprocals of factorials: 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial. And then what would be the ordinary power series, or the ordinary generating function for this sequence? Well, you would write 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, and so forth. So you just use those numbers in the sequence as the coefficients of your power series. And if you remember anything from calculus, and in fact, you want to think about, do you know a closed form for that? It's a good time to stop the video, answer these sort of rhetorical questions, or think about them. So what is this power series? This is the power series for e to the x. And the closed form for that is e to the x. It's the most famous power series from calculus. In fact, using generating functions involves calculus. And that's already amazing. Why would, in the middle of a combinatorics talks, where we're counting discrete things, where would calculus come in? But it will, and you shall see that. So this has closed form e to the x, and so we write that e to the x is the ordinary power series of the reciprocal of factorials. And the point is that the function e to the x, that little symbol e to the x, has all that sequence all itself. If I tell you e to the x and I say, well, I'm thinking of the coefficients, well, you can go back and find its power series, its Taylor series at x equals 0, or Maclaurin series, and then you retrieve your sequence. In the next in a few lectures down, we will use these to actually count combinatorial to answer combinatorial questions. Right now, we're just familiarizing ourselves with power series. So in calculus, you start with a function and you ask for its power series. So you say, well, here's a function e to the x, tangent of x, cosine of x, blah, and what is its power series? And the power series of f at x equals 0 is given by always f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared, all the way, and the kth derivative at 0 divided by k factorial times x to the k, and so on. This is the power series at x equals 0. It's also called the Maclaurin series for the function f. Or Taylor series at x equals 0. And again, the typical term, the coefficient is the kth derivative at 0 divided by k factorial. Now, in calculus, we don't worry about convergence. We worry about whether or not this thing that we wrote converges or not. And why is that? Well, that's because we are adding an infinite number of things. And when you add an infinite number of things, most likely, for example, if they're all positive, if you're just adding more and more positive things, a lot of times you'll get infinite. You'll just get infinity. You won't get anything. The amazing thing is that sometimes, even when you're adding an infinite number of positive things together, it doesn't go to infinity, and you can actually define a value for that. That's the beauty of convergence. And the point is that for that to happen, the terms that you're adding in have to get smaller and smaller. And it's not enough for them to just get smaller and smaller. They have to get smaller and smaller fast enough. But those are all topics from calculus. We not only worry about whether or not this thing converges altogether for all x, it might be that it converges for some x, but not others. For example, for x equals 0, it always will converge. If x is 0, we just have f of 0. It's not an infinite series, and so that it will converge. But depending on the function, for some x it may converge, for some x it may not. Even if it converges for an x, it may not converge to f of x. So there's plenty of functions where you can write the Taylor series at x equals 0. The Taylor series at x equals 0 converges for x equals 1, but it doesn't converge to f of 1. So those are the questions that you ask in calculus about convergence. You start with a function. How does this power series, when is it equal to the function? In combinatorics, though, we have a different point of view. We don't start with a function. We usually start, sometimes we do, but usually we start with a sequence of numbers, and we ask for the function. And we want a function such that when we take its kth derivative at 0 and divide by k factorial, we get hk, the kth term in our sequence. And the reason we want that is because then that function has all of my R sequence in it, and I can always retrieve it. I can open that function up and find out what sequence is easily. So the function encodes my sequence. But because of that, I'm not actually really concerned about analytic properties of the function. We're not really interested in knowing whether or not the function, this power series converges to the function or not, for which x, and so forth. Because the way we are thinking about it is that the function is a placeholder for the coefficients. And as long as the formal process of finding the power series of the function, finding the derivatives and dividing by factorials, gives us the coefficients, we're good. And even if it doesn't converge, we still can use that process to retrieve our sequence back from the coefficients. And so we don't worry about whether the series converges or not. Now, that's not 100% true. It's true in elementary combinatorics, in introductory combinatorics. In more advanced combinatorics, that's not true. We actually will use those analytic properties when the function converges and so forth to glean more information about our sequence. For example, about asymptotic behavior of our sequence, but not in the kinds of things that we are concerned about here. And so, in our sense, we're talking about a formal power series, not an analytic one where convergence is the question, but the fact that here's a function, and if you go through the rigmarole of finding its power series, you get my sequence back, and that's all I care about. Okay, so let's look at some examples. Let's start with the simplest sequence of all. What about sequence of all ones? Well, this sequence, its generating function by definition is 1 plus x squared and so forth. I'm putting those coefficients as the coefficients of the constant term, the coefficient of x, the coefficient of x squared, and so forth. And the closed form for that is 1 over 1 minus x. Actually, in the next slide, I will tell you why that is. But you know this from calculus possibly. So the closed form is 1 over 1 minus x. Now, it actually not converges to 1 over 1 minus x for all x. It only converges if x is between -1 and 1. But as we discussed, we are not concerned about that. And we write 1 over 1 minus x is the ordinary power series of 1 when n goes from 0 to infinity. Now, we prefer this to writing 1 over 1 minus x equals 1 plus x squared plus blah, because they are not really equal all the time. Again, the calculus comes in and tells us, for example, when x is 2, the two things are not equal. If x is 2, 1 over 1 minus x is 1 over minus 1. And if x is 2, the power series doesn't converge. It becomes infinite. And it converges only when absolute value of x is less than 1. But that's not our concern. Our concern is that we found 1 over 1 minus x, and that encapsulates, it's a placeholder for this sequence of all ones. What if we had a finite number of ones, like k ones? Whenever we have a finite sequence like k ones, we usually think about it either explicitly or implicitly, add a trailing set of zeros to make it an infinite series. So 1, 1, 1, 1, and then all zeros. Well, what's the power series for that? Well, it's going to be 1 plus x squared plus all the way to x to the k minus 1, and then zeros after that. The reason it's x to the k minus 1 is because we start with x to the 0. So that first one is the coefficient of x to the 0. The second one is the coefficient of x to the 1. And the kth one is the coefficient of x to the k minus 1. And after that, of course, it's all zeros. Okay, now what's the closed form for that? This is a partial sum of a geometric series. And you might remember again from calculus how to find that. But I want to show you quickly how you find that, because this is so basic that you really should not be memorizing a formula. You should just know how to find this. So the way we do that is we multiply by that common ratio, x. So we say that s of x was 1 plus x all the way till x to the k minus 1. Then x times s of x is x plus, one at a time, I multiply by x. X plus x squared plus x cubed and so forth. If you multiply that by x, you get x plus x squared plus x cubed all the way till x to the k. And then I subtract the two. Why do I subtract s of x and find s of x minus x times s of x? Well, because when you do that, a lot of things cancel. For example, the x's cancel, the x squares cancel, the x cubes cancel, the x to the k minus 1 cancel. The only thing that's left is the 1 from s of x and x to the k from s of x. And so we're left with 1 minus x to the k. We can factor s of x on the left and then divide by 1 minus x, and we get that s of x is 1 minus x to the k over 1 minus x, as long as x is not 1. When x is 1, then we can't divide. And so 1 minus x to the k over 1 minus x is the ordinary power series of a sequence of k1s, n going from 0 to k minus 1. Now, if absolute value of x is less than 1, and if you let k go to infinity, then this term x to the k goes to 0. If you have a number less than 1 and you keep multiplying by itself, it becomes smaller and smaller, goes to 0. And if that goes to 0, you're left with 1 over 1 minus x, which explains the previous slide, why the sequence of all ones, its ordinary power series was 1 over 1 minus x. Okay, let's move on to another example, and let's look one that's that comes up in combinatorics a lot, binomial coefficients. So let's look at one row of the Karagi-Gia triangle. Karagi-Gia triangle is the triangle that almost everyone calls the Pascal triangle. So n choose 0, n choose 1, n choose 2, n choose n. N is some positive integer. What is the generating function, the ordinary power series for these numbers? Well, what you have to do is you write it up. By definition, is just this: n choose 0 plus n choose 1x plus n choose 2x squared plus n choose xn. And as I said, we think of an infinite number of trailing zeros. Now, you could act smart to say, oh, well, there is the ordinary power series, and you would be correct. But usually when someone asks you for a generating function for a sequence, they really are asking you, can you find it in closed form? They can always themselves write it as a power series themselves. They wouldn't have to ask you. Okay, so what is that? Well, here we need some of the work we've done before. This comes from the binomial theorem. The binomial theorem, the closed form of this polynomial is 1 plus x to the n. 1 plus x to the n expands exactly as that. And so 1 plus x to the n is the ordinary power series of n choose k, k going from 0 to n. We can also say that's actually the ordinary power series of n choose k when k goes from 0 to infinity. And sometimes it's more convenient to have infinity up there than n, because then manipulating things becomes easier later. Why can we say that? Well, the reason for that is that as soon as k goes above n, then n choose k becomes 0. And so these two sequences are the same. Okay. For our last thing, we will have a preview of what we're going to do in our third lecture in this series, which is to find new power series from old. So we've found that 1 over 1 minus x is the ordinary power series of the sequence 1. This is the right way of writing it, because we are focusing on the fact that this is the power series. We're not talking about equality, but it's actually more convenient to write 1 over 1 minus x equals 1 plus x squared and so forth for the purpose of what I want to do next. I'm going to write that even though this is an abusive notation, because the two sides aren't really equal all the time. It depends on x, as we have been discussing. If x is 2, for example, the two sides definitely are not equal. So the better way of writing it, the more correct way of writing it is this. But if you write it as 1 over 1 minus x equals that, and it's true for some values of x, then manipulating it becomes a lot easier, or easier to see what we're doing. So you start with that, and you can do things with it. Like, for example, you can take derivatives of both sides. 1 over 1 minus x is the same as 1 minus x to the minus 1. And so the power rule tells you, together with the chain rule, that it's minus 1 times 1 minus the derivative, 1 minus 1 times 1 minus x to the minus 2 times the derivative inside, which is another minus 1. So you get 1 times 1 minus x to the minus 2, which is 1 over 1 minus x squared. So that is the derivative of the left side. The derivative of the right-hand side, well, the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, and so forth. So we get, we see that we have now a power series for a new sequence. So we now got that 1 over 1 minus x squared is the ordinary power series for n plus 1, n going from 0 to infinity. Why n plus 1 and not n? Because n is not the coefficient of x to the n. In this power series, n is the coefficient of x to the n minus 1. The coefficient of x to the n, which is the next term, is n plus 1. And n goes from 0 to infinity. When you plug in 0, you have 1. When you plug in 1, you have 2, and so forth. If you wanted the ordinary power series of n, then all you have to do is shift these guys. And you do that by multiplying by x. So if you multiply both sides of this new equation by x, you will get x over 1 minus x squared equals x plus 2x squared plus 3x squared plus nx to the n and so forth. And so the typical term now, the coefficient of x to the n is n. And so now we have that x over 1 minus x squared is the ordinary power series of the counting numbers 1, 2, 3, 4, 5, 6, whatever. And 1 over 1 minus x squared is the is for n plus 1. Okay, well, actually, I said this slightly wrong. So the x over 1 minus x squared is the ordinary power series of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 over 1 minus x squared is the ordinary power series of 1, 2, 3, 4, 5, 6, 7, 8, 9. But we can continue. We can take the derivative of both sides again. And now you have to use the quotient rule from calculus and simplify. And if you do that, you get 1 plus x over 1 minus x quantity cubed. And the derivative of the right-hand side is easy. It's 1 plus 2, the 2x squared. This derivative is going to be 4x, which is 2 squared x, then 3 squared x squared, and so forth. And so that tells us that 1 plus x over 1 minus x cubed is the ordinary power series of n plus 1 squared. Again, the coefficient of x to the n is not n squared, is n plus 1 squared. But if you wanted n squared to be the coefficient, this starts with 1, but if you wanted to start with 0, then you just multiply by x. So if you multiply by x, you get that x times 1 plus x over 1 minus x cubed is the ordinary power series of n squared. So if you have the sequence 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, then the ordinary power series is x times 1 plus x over 1 minus x cubed. That's the end of this, this lecture. In the next lecture, we'll talk about what happens when you multiply two power series. In the third lecture in this mini series, we will talk more about manipulating power series, and then we will move on to using power series for combinatorial arguments. Till next time.